But what's it all about, Basil? Why are we studying these series? Tell me. The answer is right here. Okay, this is one good reason why series are so helpful. Look at this guy. We're going to learn, first of all, in this first example, that you don't always have to create from scratch a series. Once you create a series, you can mess with it to become a different series for another function, just like we did, I think it was section 9, that difficult section where you're trying to make everything look like 1 over 1 minus x, right? Anyway, so this is saying find the MacLaurin series for this function. Now here's the thing. I don't know what page it is. I can look it up in chapter 11, but there is definitely a table of MacLaurin series, and I believe that it is in section 10. Let me see. Oh, I'm almost there. I'm almost there. I think I passed it. No, I didn't. Where are you? There's a table here somewhere. There it is. Page 768. So page 768 is a table of MacLaurin series. Now, what's the story with MacLaurin series again? Right? Do you remember? They are centered where? Centered at A is 0. That's right. So there's a table of MacLaurin series on this page, and one of them has to do with sine. Now, I don't think I developed sine. I did cosine, didn't I? Well, I'll tell you what sine is. Sine looks like the following. It starts at x instead of 1, and then it's minus, and it goes through the odd powers, x3 over 3 factorial, x to the 5 over 5 factorial, minus, and it alternates. So it would have a summation notation that would look like, almost like cosine. Goes something like this, goes to infinity. You've got that minus 1 flickering, but then you've got a power of x, which in this case I think is 2n plus 1 if I'm not mistaken. That's good. And downstairs is 2n plus 1 factorial. What's the, that would be for sine. Compare it with cosine. Cosine of x, if we had to use that one, would be n is 0 to infinity. It's minus 1 to the n, and the only difference is it goes x to the 2n only, 2n factorial. This guy goes through the power 0, 2, 4. This guy's going through the powers over here, 1, 3, and 5. And put them together with all pluses, you got the power series for e, which the exponential e. Pretty good stuff. Why am I saying all this? You can steal these series and you can build other series. I'm going to build this one before your very eyes. You ready? So we can go sine of x cubed all over x, right, is equal to, well, 1 over x times the series, n is 0 to infinity, and I'm going to plug this guy in for x in the series, and it looks like this. Okay, this says minus 1 to the n. I've got something to the 2n plus 1 all over 2n plus 1 factorial. And what we're plugging in is x cubed. Okay? And so let's finish it off. What we'll do is we'll bring this guy in and have it multiply inside because it's like he's distributing with every term. And here's your series. N is 0 to infinity. We've got the minus 1 to make the signs change. Oh, I forgot to multiply. What power of x is that? That's a trip. We've got 2n plus 1 factorial. Work on that power for me, would you, while I write this down. It is x to the, 6x plus 3. But then we're dividing by x, so really 6x plus 2. There you go. That's the series for sine x cubed over x. Woo, that was fun. Let's do about 10 more. Not really. What I'm going to do is the next problem. Well, look at this. Ready? We got a series for a strange function. Look what it's good for. Okay. We want to approximate this particular integral using the series we just built. Okay? So how's that done? Well, what we're going to do is we're going to integrate this series. And when I integrate this series, what I'm going to do is string out enough terms so that I'm going to have enough terms to be a very good approximation of the answer. And that's how power series work. You don't go to infinity. It approaches at infinity the function you're mimicking, but you go out as far as you need to. If you want a certain degree of accuracy, you go out several terms and you've got it. And if you put it in a computer, boom, that's how it's done. Okay, so what we're going to do is we're going to say, okay, so the integral from 0 to 1 of sine x cubed all over x dx is the same as integrating from 0 to 1 our series. But since I'm going to approximate with it, I'm going to write out some terms. Ready? So if n is 0, it's positive, and it's x squared all over 1 factorial. The next one is minus. When we plug in 1, this is, oh, I made a mistake. There's an n right there. I've been making mistakes, goodness gracious. I saw a mistake on the last video. Okay, we'll fix it. Okay, anyway, so that's an n. So we're plugging in 1, we get x to the 8th over, that would be 3 factorial, okay? See what I'm doing is I'm looking at the terms. X is equal to what, 2? Okay, it's positive. And we've got 14, so x to the 14th power all over 5 factorial. Let's do one more. Minus x to the, this would be 20 over, that would be 7 factorial plus. And as far as you want to go, that's what you do with power series. You can integrate a polynomial. Integrating this guy, good luck. I don't know how it's done. Good luck to you. But with a polynomial, it's super easy. Check my work. All right, so what we're getting, now here's the thing. We're going to integrate. So we're going to get x cubed, right, over 3 minus x to the 9th over 9 times 3 factorial plus x to the 15th over 15 times 5 factorial minus x to the 21st over 21 times 7 factorial plus, and keep going, and guess what? We're going to apply these limits. We're going to apply the limits on this guy, right? So we apply the upper limit and we get, it's just 1. I'm just plugging in 1. By the way, the interval of convergence for sine is the same as cosine, all real numbers. So you can plug in anything you want, but the closer to the center, the better, the quicker it converges. Here we're plugging in 1. This guy is centered at 0 and we're plugging in 1. So we got 1. I'm going 1 cubed over 3 minus 1 to the 9th over 9 times 3 factorial plus 1 to the 15th over 15 times, why do you keep on saying that? 1 to any power is just 1. Minus 1 to the 21st, 1 times 1 times 1, is 1 over 21 times 7 factorial plus, okay, that's the upper limit, but what you notice when you plug in the lower limit, when you plug in 0, it's just a bunch of 0 plus 0, and he's gone. What are we left with? An alternating series. What do we know about alternating series? Well, we can figure out how close we are using the alternating series error estimate. Okay, so I'm going to save a little time here. The first term, okay, the problem says 4 decimal places. So we want the error less than 0.0000, let's say 5. Okay, I checked these two guys, and the one that works first is this one. He is less, I forget what I got, some really small number. Had a bunch of zeros, 0.00005. He's the winner. So, do you remember what to do? Our estimate, you add up all these 3 numbers. So when you do that, you go, this integral is approximately 1/3, right? Minus 1 over 9 times, that's 6 by the way, plus 1 over 15 times 5 factorial. And what I got there when I punched that through was 0.31537, 0.31537,037. Okay? Yes, it's not the exact answer, okay? But it's a good approximation, and by theory, it should be good for 1, 2, 3, 4 decimal places. So the answer is good. 0.3153 for sure is accurate. If you want it to be more accurate, add more terms, okay? Pretty cool stuff. And so what you could do to check this, by the way, is go ahead and Google like a definite, if perhaps you've done this before, integral computer, if you will, or calculator, I think they call it. What's a popular one? Wolfram. There's others. And punch it in and see what you get. The best part about this is that you're doing it by hand, what the computer is programmed to do. And so we're gaining an understanding of how this works. Okay, I got one more example here. This is actually from section 11. There's not much to section 11. You should just throw them together, I think. But anyway, or put the applications all together in one section, maybe. But I'm going to do this last one with you guys, and it is cosine centered at pi. Does that sound familiar? That's where I made my mistake, by the way. But we're going to estimate cosine of 170 degrees, correct to 5 decimal places, okay? All right, so the way this works is, first of all, we bring down your series, right? So let's go up here and fix the mistake. Where did I do that thing? It was on the edge up. I like that problem. That was cool. It was this one. It should have been, oopsie daisy, that's a 4 factorial, and this is a 4. Okay, so that's the series we're going to use. This is cosine centered at pi, okay? Remember it, okay. It goes by the even powers, except the signs are all switched. Did you notice that? Okay, last one. So way down here. All right, so let's write that down before we forget. So cosine of x at a is pi gave us -1 plus x minus pi, what, squared over 2 factorial minus x minus pi to the 4th over 4 factorial. And if we need it, plus x minus 4 minus pi to the 6th, right? I keep doing that. Okay, minus pi to the 6th over 6 factorial minus, and you as many as you need. What we're going to do is we're going to evaluate cosine of 170. The first thing you do when something in degree form comes into a calculus realm, in the realm of calculus, we put it through the switch to radians machine, okay? So you take the 170 degrees, multiply it by 180 downstairs and pi upstairs, and you get like, what are you looking at there? You got 17/18 pi? 17/18 pi. That's another name, of course, for 170. I have to do that because now we are going to plug it into our function. So we're going to say cosine of, and I'll do this in red, 17/18 pi, okay, is equal to -1. Now I'm going to the power series, okay, plus this guy minus pi squared over 2 factorial minus this guy minus pi to the 4th. And this is the machine, the polynomial machine that does our approximating for us. And the beautiful part about this, so wonderful, is that you can go as far as you want for as much accuracy as you want. 17/18 pi all the way through. Do you see what I'm doing? Just plugging it into the machine. It's a function. It's a polynomial function that has many terms to it, okay? And we could say that by going minus if we need more. Okay, so we are going to approximate this guy, and it's an alternating series, notice. So we want the error less than, where did they say, 5 decimal places? So 0.00000 and then 5. Okay, and of course, now here's the thing for you guys as you're doing your work. Our answer, cosine of 170 or 17/18 pi, what I do first is I do the math in the parentheses. Look at that. What we have really is plus negative pi over 18, is that right? Squared over 2 factorial. Be careful, be sure to do that. Minus, this is, yeah, it's minus 1/18, so pi over 18 to the 4th over 4 factorial, maybe one more plus minus pi over 18 to the 6th over 6 factorial minus if I need more. Well, yours truly did this problem also, and he found that this guy was the first one that was less than 0.000005. So the summation is this. Okay, and I won't bother to write it out again. I'll just simply say that cosine of 170 degrees, now I'm cleaning it up for the folks around us, is approximately, and then you add, this is your sum right here, these three terms. I got as a result minus 0.9848 minus 0.9848, 07792, 07792, okay? And then if we reach for the calculator and we switch it to, say, degree mode, okay, and then we say, hey man, wake up, yeah, I want cosine 170. What you got for me? It says for the calculator, gives us this answer, negative 0.98480 7753. Where are we going wrong? Let's see. Back here. Okay. Look at that. 1, 2, 3, 4, 5, 6, 7 decimal place accuracy. Isn't math wonderful? And that's the last video of chapter 11 for you guys. Enjoy all that crazy calculating. And there you go. We'll see you at the next one.